Yeah, let me start by saying that this is based on joint work with Jose Burgos, who will talk next, and also partially with Partit Sombra. So let me start by giving you the outline of the talk. So I'm going to start by giving you some motivation about why we got started studying these objects. And then I will talk about b-divisors, where B, I'm just going to start by saying this, B stands for birational. And then I will focus on toroidal b-divisors. These are some special kinds of b-divisors which have the property, or they are good because they enjoy convex geometrical properties, and their intersection theory can be studied via tropical methods. And so they are very nice to work with. And at the end, I will go back to the motivation by giving you a small example. And I think Jose in the next talk will give you more details about an application of this theory. So let me start with the motivation. So the main motivation is the so-called Chern-Weil theory. So we start by considering X a complex manifold of dimension n, and E a holomorphic vector bundle on X. So giving this, you can consider the so-called Chern classes. These are some topological invariants which measure in some way how far E is from being trivial. And then Chern-Weil theory says, or that the Chern classes can be represented by means of geometric data. So in terms of currents and forms in the RAM cohomology. So an example where Chern-Weil theory is satisfied is if you consider a smooth Hermitian metric on your vector bundle, then the Chern forms represent the Chern classes in the RAM cohomology. Now, smooth Hermitian metrics exist, but usually the metric which you are given in the problem you're studying is not smooth. So a lot of effort has been put into trying to generalize Chern-Weil theory to more singular metrics. And a first result in this direction was given by Mumford in the 70s. And he says, so if you consider your X compact and you have an open then subset on X, and you have a smooth Hermitian metric on your open, but in such a way that your extension of the metric to the whole compact space is good as a singular metric. So this goodness, this is an assumption on the asymptotic growth of the metric when you approach the boundary. So this gives some mild singularities, which sometimes are also called logarithmically singular. And then Mumford's result says that in this case, the singularities are so mild that the Chern currents represent also the Chern classes in this case. So in particular, if your vector bundle is of rank 1, then you can compute the top intersection number on this compact space in terms of top wedge products of smooth differential forms on your open set. So this is a nice result, and it gave a lot of applications. In particular, this enabled Burgos, Kramer, and Kuhn in 2005 to develop an oracle of intersection theory of automorphic vector bundles on pure Shimura varieties of non-compact type. So, for example, on AG. So a natural question is, what happens if now you consider families of abelian varieties? What happens if you consider the universal abelian variety? So here you have automorphic vector bundles which come with invariant metrics, and you can ask, does Chern-Weil theory also is satisfied for these kind of metrics? And the question is no, and the first example was given also by Burgos and Kramer and Kuhn in 2014. And their example goes as follows. So they consider the universal elliptic curve Yeah, so you have here your universal elliptic curve, and this lives over the modular curve. So here you have with a level n structure, so you don't have to worry about stacks. But then a point here represents an elliptic curve with some level n structure, and then and then over on En, you can consider the line bundle of Jacobi forms, which come with two invariants k and n, weight and index. And this line bundle carries a natural metric with canonical invariant metric H. And then recall that Chern-Weil theory was a statement about computing smooth differential forms. So this H is smooth on En in terms of a compactification. So here you can consider the toroidal compactification, which you get, which is modular, and you obtain by adding the so-called cusps of your modular curve, and over each cusp, you have such an n-gon. And then it turns out that your line bundle together with the metric extends to the compactification. And the extension as a semi-positive metric is unique, but the problem is it's no longer good. So along these double points, the metric acquires some singularities which are not good, so are worse than log singular. And this implies that if you take another toroidal compactification, so here, for example, you blow up one of these double points, and you take this other toroidal compactification, then the extensions of the metrics of the line bundles together with the metrics are not compatible. So you have here you have your second toroidal compactification, and then the pullback is not the other one. And this implies in particular that the top intersection numbers depend on the choice of a compactification. So in particular, Chern-Weil theory is not longer satisfied for these kinds of metrics. So Chern-Weil theory is not satisfied for H. So the idea they first had in this example, Burgos, Kramer, and Kuhn, was to consider all compactifications and compactify your line bundle together with a metric, not as a line bundle, but as a B object, so as a b-divisor, which lives on all compactifications. And moreover, in this case, you can consider, it's enough to consider all toroidal compactifications and compactify your line bundle together with a metric as a toroidal b-divisor and use convex geometrical tools. And with this idea, together with Burgos, Holmes, and de Jong, we obtained Chern-Weil type results and asymptotic dimension formulas for spaces of Siegel-Jacobi forms. But about this, Jose will tell you the whole story. So this was the motivation. And now let me then talk about b-divisors. So b-divisors, they were first, I think, studied by Shokurov in the early 2000s. And since then, a lot of people have worked with b-divisors, and I think they are becoming more and more important because people are realizing that they are nice objects to work with. And so the definition is as follows. The setting is you start with X, a smooth projective variety over an algebraically closed field K of characteristic 0. And then you consider your set R of X consisting of all smooth and proper modifications of your variety. So this R of X has, you can put an order in it. So you say that one modification is bigger than the other one if there exists this map, which is necessarily irrational and proper between both modifications. And so this R of X becomes a directed set. And then you define the group of Cartier b-divisors as the direct limit over all such modifications of divisors with real coefficients on your modifications. So with maps given by the pullback map of divisors. And you endow this with the direct limit topology. And then the group of wild b-divisors on X is the inverse limit over all such modifications with maps given by the push forward maps. And you endow the space with the inverse limit topology. So maybe to be a bit more concrete, or to be able to represent such an object, a wild b-divisor, you can see it as a tuple. So this is a tuple of divisors indexed by modifications, and they have to satisfy that they are compatible under the push forward map. So given such a modification bigger than the other one, you have that the push forward map of the bigger one is again the other one. And then a Cartier b-divisor is going to be a wild b-divisor, but which is finite in the sense that it is determined on a single model. So there exists a model pi such that any other model above it you can obtain by pulling the one where it is determined. So maybe here I say a bit about the topology. So we endow these are topological spaces, and the strong topology of Cartier b-divisors is not the subspace topology of the weak topology. So this is not true. The strong topology is much stronger. So, for example, a limit of Cartier b-divisors converges in the strong topology if all of them are determined on the same model, and on this model they converge coefficient-wise. And the weak topology, a sequence or a net of b-divisors convergence if in all models they converge coefficient-wise. So these are different. And as you may see already, the space of wild b-divisors is very, very big. So you can, in principle, start with your variety and start blowing things up. And along the exceptional divisors, you can put any coefficient you want. So you have absolutely no control of the coefficients which are appearing new. So what we will want to do is to do some intersection theory. And it's some positivity assumption. And it turns out that the Neff-ness assumption is going to be a very nice positivity notion to work with. So you say that a Cartier b-divisor is Neff if it is Neff on a determination, and a wild b-divisor is Neff if it is a limit in this weak topology of a net of Neff Cartier b-divisors. So it was very recently shown by Dang and Favre that if your b-divisor is Neff, then it is not only a limit of a net of Neff Cartier b-divisors, but it is a limit of a monotonic sequence of Cartier b-divisors. So this is being approximable, and hence it has a well-defined degree by defining the degree just as the limit of the degrees of the Cartier b-divisors in such a monotonic sequence. So this is good. Okay, so now now I will talk about these so-called toroidal b-divisors. So first, I'm going to say what a toroidal structure is. So a smooth toroidal structure on X is the choice of a smooth modification, pi1, and a simple normal crossings divisor D on X1 containing the exceptional locus of pi1. And then you can consider the inclusion of the open set by removing this boundary. And this is an example of a toroidal embedding without self-intersections. So in the sense of Knudsen, Mumford, and Saint-Donat. And to such a toroidal embedding, also by their theory, you can consider the associated conical polyhedral complex. So this is an example of an abstract polyhedral complex in the sense that this does not live in a vector space, in any specific vector space, but each of the cones lives in a separate vector space. And the set, so this space, this toroidal embedding is going to be stratified, and the strata is in order reversing bijection with a set of cones. So example thereof are typically then the toric varieties. But then you can consider several toroidal structures giving an algebraic variety by any choice of a simple normal crossings divisor. So we want a notion that compares two toroidal structures. So if I have two toroidal structures, x1d and x2d prime on X, then we say that x2d prime is above x1d if this modification by two factors, as in the diagram over here. Yeah, in such a way that the inverse of the boundary divisor in x1 is contained in the boundary divisor of x2. So maybe here I give a small example. Well, as I say, you can consider a lot of different toroidal structures. For example, if you start with P2, then you can consider the toroidal structure given as by P2 as a toric variety. So you can consider D prime X without the torus, and then the corresponding polyhedral complex is going to be a fan. In this case, so it's is the fan of the toric variety. And then, but you can on P2, you can also consider the toroidal structure, for example, given just by two hyperplanes, right? And then here, the polyhedral complex is just going to be this positive orthant. Yeah. So there are many different choices, and we're going to come to this a bit later. But the point is, if now we are going to fix one toroidal structure, and we're going to define toroidal b-divisors with respect to a fixed toroidal structure. So this is fixed, and then we define the set of all toroidal modifications of X with respect to this toroidal structure. So these are some special modifications, which are the toroidal ones. So roughly, you can just blow up closed strata, and then these correspond to the subdivisions of your conical polyhedral complex. And then the group of toroidal criteria b-divisors with respect to this toroidal structure is then defined as the direct limit over all such toroidal modifications of the space of divisors with real coefficients supported on this boundary. And the group of toroidal well b-divisors on X is going to be then the inverse limit with respect to the push forward maps of divisors supported also on the boundary. And so the first result I'm going to state is a characterization of toroidal b-divisors. And so there is a homeomorphism between the space of toroidal b-divisors with respect to the given toroidal structure with the space of conical functions on the set of rational points of your polyhedral complex. So maybe just here again with the analogy, if you start with a toric variety and you start with a toroidal structure just given by the toric boundary, yeah, that this space is just the lattice, the dual of the lattice of characters of the torus tensored with Q. Yeah, so here you obtain all conical functions on and Q. And so the homomorphism is defined by taking D, the b-divisor, to the function, which is defined by taking such a primitive vector. And then the primitive vector is going to be associated to a prime divisor on some modification, and then you take the coefficient of your b-divisor along this prime divisor. So this is just a generalization of the typical toric case. And then under this identification, the space of Cartier b-divisors corresponds to the subspace of piecewise linear functions. So here already you see that that this space also in this toroidal or also in the toric case is very big. So all possible conical functions. So conical just means that phi of lambda x is equal to lambda phi of x for positive real numbers. But this, I mean, these are a lot of functions. They are not, you don't impose any continuity or anything. These are all functions which only satisfy this. So here you don't have any kind of control of these functions. So in order to do some intersection theory, we need this Neff-Ness assumption. So we'll come to a characterization of Neff b-divisors. But before this, I'm going to say the following fact, and is that given a toroidal structure on X, we can always find a second one above it whose combinatorics captures the intersection theory of boundary divisors. So what am I saying with this? So what I recall that a toroidal this conical polyhedral complex, this is an abstract thing. So this does not live in a vector space. And what we want to do is to do tropical intersection theory in order to obtain information about intersection numbers of these toroidal divisors. Then what we need is some kind of balancing condition on these toroidal, this conical polyhedral complex. But for this, we need a vector space where we can define this balancing condition. So there is this notion given by Gross. So there exists a natural, given such a toroidal structure, there exists a natural weak embedding. So this is just a map from your conical polyhedral complex to some canonically defined vector space. And this is such that the restriction to each of the cones is linear. Yeah. So, and here you can define then through this embedding, you can define a balancing condition. Okay, but now, for example, in the example we had before, where we had this toroidal structure given by the two hyperplanes, for the toroidal structure given by the two hyperplanes on P2, then this weak embedding looks like this. It goes, so there is not enough information. So this vector space is just the real line. So you're losing a lot of information. You're not recovering the whole information you need in order to have the information about the intersection theory. But then the thing that we proved is that you can always find another toroidal structure above it, such that, so there exists a toroidal structure above it, above XD, such that this weak embedding is such that the restriction to each of these cones is injective. Okay, and this property, which we call that it's a quasi-affine embedding, a quasi weak embedding, quasi embedding, I think. Then this property says that you have enough information to recover the intersection theory. And then one such polyhedral, conical polyhedral space, with the property that this weak embedding is a quasi embedding, so it's injective. Yeah.
quick question. So are you saying you can modify?
I'm sorry, can you repeat the question?
Like, will it be injective on the cones, on all the cones? Or
on all the cones.
On
all
cones?
the cones, yeah.
Oh, okay, cool.
Yeah, for all cones. For all cones. And then
there also is a question in the chat asking what this says for MG, or whether it applies to the setting of moduli spaces.
Maybe we can come to this, but there in principle you have the same definitions. You have toroidal b-divisors. I mean, you have the toroidal compactifications. The linear Mumford, this is a toroidal compactification, so you can consider in principle toroidal b-divisors in this context as well, of course. Yes. And then okay, so and such a conical polyhedral space, such a conical polyhedral complex where you really have this balancing condition and this property that when restricted to the cones, it's injective, is called or is what we called an example of a conical polyhedral space. And then the characterization of toroidal b-divisors is as follows. So assume we are in such a good conical polyhedral space, and then you consider a b-divisor, which is Neff. And then the statement is that this b-divisor corresponds to a so-called weakly concave function on this polyhedral space. So let me maybe come to this now. So weakly concave. So we are now talking about this conical polyhedral spaces, which are polyhedral complexes with balancing condition. And then there are, I mean, you have a notion of concavity on a convex set, but in principle, you don't know what a good notion of concavity is on such a polyhedral space. And this was studied in joint work with Martin Sombra and with Jose Burgos. And it turns out that there are basically 3 different notions of concavity on such a space, which are different and which are all nice to study. And they are based on, in the piecewise linear case, they are based on preserving some positivity of with respect to the tropical intersection product.
Ask there's another question in the chat.
Yes.
I think relating to the previous slide, these modifications, whether you can think of them as iteratively blowing up all strata of this D.
No, I mean, your X is fixed. What you're doing is you're adding more divisors to your boundary. That is what happens. I mean, your X is fixed. You're not blowing up anything. You're enlarging your toroidal boundary in such a way that you make always fixed. There's always the same X. You're not blowing up anything. You're just modifying the D. So you're making the U, so the X.
You make the U smaller than, yes.
Exactly. You're adding boundaries. Yes?
Yeah, I see. Thank you. Thanks.
Okay. So to this weakly concave function, so this is defined in such a way that it preserves some positivity with respect to the tropical intersection product for piecewise linear functions, and then you can extend this to all functions. And what we showed is that such weakly concave functions are also enjoy continuity properties as in the classical case of concave functions, so they are also continuous, for example. So in the case, maybe I here make as well the analogy with the toric case. So if X is toric and your D is just this boundary, then weakly concave function on a on Rn is the same as concave function. So all three definitions are the same on such a fan. And then this is just a concave function on your fan. And then to this weakly concave function, you can associate a Monge-Ampère measure supported on a compact set. So in the toric case, this Monge-Ampère measure is going to be the classical Monge-Ampère measure associated to a concave function. So concave. Yeah. And then the degree of the b-divisor is going to be computed as the integral of this weakly concave function along this compact set with respect to this Monge-Ampère measure. So in the toric case, this is just the integral of the concave function with respect to the Monge-Ampère measure of the concave function, which is just the volume of the stability set of the concave function. Okay,
actually,
so
may I just go back to the other question again? So when you think about a toric variety, shouldn't you be, I mean, these modifications that you talk about, are these actually like toric blow-ups in this case? Or did I misunderstand something in your answer earlier?
I think so, because I mean, what we're doing here is we're not blowing up X. We're just enlarging your simple normal crossings divisor.
By adding extra points, like another prime divisor in X to it.
I mean, like in this case, you have H1 and H2. And here you can enlarge it to D prime or to D, 2 prime, just the whole thing. To adding the other hyperplane.
I see. This is the type of operation.
Exactly.
Okay, sorry.
Exactly.
Okay, thanks.
So the statement is that you can compute this degree in terms of these Monge-Ampère measure generalizing the classical Monge-Ampère measure associated to a concave function. And then the other thing is that we also have a Hilbert-Samuel formula. So if we start with a b-divisor toroidal, which is Neff and big, I will come maybe to big later, then your degree can be calculated in terms of the volume. So about the volume, so to D, you can associate graded linear series. RDL is just rational functions such that d of f plus d is bigger or equal to 0. So this gives you a graded linear series, and this graded linear series it has the property of being something that is called of almost integral type, which means that is contained in something that is finitely generated. And then the theory of concave bodies gives you an concave body associated to this graded linear series. And you define also the volume of the b-divisor as the volume of these graded linear series. And then here you have also that this is the same as the volume of this concave body. But then maybe there is another question in the chat, but maybe before I just want to say here a remark that is this volume function is continuous in the set of and you say that a b-divisor is big if the volume is strictly positive. This is just the generalization of the classical definition. And then the volume function is continuous in the set of big and F toroidal b-divisors. And this is not the case for not toroidal ones, not the case for non-toroidal. So this is something that is particular to the toroidal case and which turns out to be very useful again, we will see this maybe in Jose's talk, for computing some asymptotic dimensions of rings of automorphic forms. But this is then an important property that is satisfied in the toroidal case and not in the non-toroidal case. So was there a question? If not, then what we also want to do is we want to compare toroidal and general b-divisors. I mean, we would like to say if you're given a b-divisor, we would like to say, oh, this is toroidal with respect to one toroidal structure. And this is, I mean, at the beginning, it was not at all clear that you can do this, but it is a fact that there is a canonical inclusion from the set of toroidal b-divisors with respect to this fixed toroidal structure into the set of general Weil b-divisors. So note here, note that there is actually a canonical projection, but going the other way around. No, there is a canonical projection from the set of Weil b-divisors to the set of toroidal ones for one fixed toroidal structure. Yeah, because the toroidal modifications are contained in the set of all modifications. So this projection is canonical. But the thing is that there exists a section. Yeah, and this is not clear. I mean, it was not clear for us how to do this, but this comes from this relation of toroidal structures, one being above the other, because it turns out that if x prime d prime is above xd, then you have such a map R from one conical complex to the other one. Yeah. And this map, which was given actually by Martin Ulrich also in a lot greater generality and maybe in some other context, but this map is in this case very explicit, and the existence of this explicit map in this case enabled us to define this section. So we have an inclusion from here to here, and then we can say that a b-divisor is toroidal if it is toroidal with respect to any toroidal structure. Yeah, so we can here really define the set of toroidal b-divisors as the direct limit of toroidal b-divisors with respect to this order given by one structure is bigger than the other one. So maybe here I also make a remark. So note, any Cartier b-divisor is toroidal. Yeah, this is by resolution of singularities. Any Cartier b-divisor is toroidal with respect to some toroidal structure. So this gives you then a relation between. So you see that these toroidal b-divisors they lie in between Weil and in between Cartier. And in between Cartier. So you can think of them as enjoying some kind of finiteness property. Yeah. And of course, these are all strict inclusions. Okay, so this I think this is what I wanted to say about toroidal b-divisors. And now let me go back a bit to the motivation and go back to the example we started with. So before I draw the picture, now it is here, but you recall that we considered this universal elliptic curve and its toroidal compactification. So this is already the toroidal compactification, which you construct by adding these endgons above the cusps. And then on this universal elliptic curve, you can consider this metrized line bundle of Jacobi forms and its unique extension to this compactification in such a way that this extended metric is a singular semi-positive metric. So Jose will mention a bit more about this, but this extension as a positive metric is unique. And then the problem was that this was no longer good in the sense of Mumford, because along this double points, it acquired some bad singularities. And then this implied that we don't have functoriality. So the extension depends on the choice of the compactification. And then the idea was to compactify this line bundle together with the metric as a b-divisor. So there is that was the motivation. Now it turns out how this procedure is done. Yeah, this is going to be explained by Jose. But the point is, in this case, you can compactify it not only as a b-divisor but as a toroidal b-divisor. Okay, in this case, this H here has the property that that it is a toroidal thing, and the corresponding b-divisor is going to be toroidal. So you can use this whole theory which I was talking about before. So maybe here we can make an explicit example. Maybe I do. So recall here, these are these double points. And then the conical polyhedral complex associated to this specific toroidal embedding, well, it's going to consist of 4 two-dimensional cones, each corresponding to one of these double points. So let me give you the local picture around one of these double points, and we can see what it's doing in terms of toroidal b-divisors. So here this corresponds to this two-dimensional cone, and these toroidal blowups then correspond locally just to inserting rays, right? You start blowing up and blowing up and blowing up and blowing up and so on, and you never stop. So really you need to exhaust the whole positive orthant. And then it turns out that this b-divisor, which is going to be defined in terms of the metric, this is going to be, so locally is given by the function, which in this case is the function given by minus xy over x plus y on this cone, and this is a concave function. So what we're doing here, if you're looking at the convex picture, is you're starting with a simplex, and by blowing up, what you're doing is you're taking off little simplices. Yeah. So you're taking off these little simplices. Okay, I don't know if, so here you're always taking off little simplices, and at the end, you're obtaining this convex object here. And the point is that the volume of these convex objects is double point. So if you think, then the degree of this b-divisor is going to be, then what you're doing is you're taking one compactification and then you're subtracting these whole residues of the metric along these double points. And then as you're subtracting these residues, then at the end, what you're obtaining is the integral of the forms along the open set. So this formula here, which is exactly the Chern-Weil type statement we wanted to see. And then maybe I do some important remarks. And important remarks is the first one. For the Chern-Weil type statement we had before, this toroidal property is not necessary. So you can prove such a statement without the b-divisor being toroidal, just for the general case. The toroidal property comes in when you want to use the Hilbert-Samuel formula in order to compute this asymptotic dimension formula for rings of Jacobi forms. So here the toroidal property is necessary. And then a second remark is that this example is really not Cartier. So this b-divisor does not live on any finite model. You really have to consider the whole tower. So just as an example, we computed here the top intersection numbers in this compactification, and the difference here. This is, well, not zero. But yeah, I think that's what I wanted to say. And yeah, if there are any further questions, I'm happy to answer them. And thank you very much.